There's food. First thing, it's a good sign.
I got a new folder because all my folders are wrecked.
Oh, hey! Yeah, should I be filming this?
I don't know.
This kid's filming everything.
Yeah, probably. Why are you aiming that thing at me?
Trying to get that action. Oh, smart kid. Probably like
This kid's like, why are they videotaping me? This kid is videotaping me right now. I don't like this.
Oh, girl, I guess right.
See ya.
Excuse me.
You gotta get a chair. Watch yourself.
Go grab that chair.
I just wanted to, make an introduction, the first thing, and I'll be covering a little bit of what are the questions that are driving us in particle physics, or what are the things that we're studying. I'll also then tell you a little bit about this standard model, or the theory that we have so far achieved to describe all these type of phenomena, very, very small and very, very high energies. And then I'll go into a little bit of detail of what the Large Hadron Collider is, how it works, and then how we actually record those collisions with this compact muon solenoid detector, the CMS detector. And then I'll try to explain a little bit what we're going to do later in the afternoon with these computers to analyze these W and Z particles decays as they decay, and these events that we've recorded in the detector. And then I'll say a little bit about the tool that we're going to use, which is this event display that is called iSpy. And then in the end, the goals for today is to actually perform a few measurements. So your job will be to basically distinguish whether the event that you have in your screen is a W production or a Z particle production. Then you're going to tag whether the W is a positive one or a negative one. This is the electric charge. Okay? And then we can measure the ratio, so how many W pluses we produce as opposed to W minuses. You will also see how these W's decays and the Z bosons decay, and whether they produce an electron or a muon, and we can also measure that, and that also tells us something very interesting about nature. And finally, once you've tagged all these C candidates, we can measure their mass, and in the end, basically make a measurement of what that mass is, which is also a very useful parameter in all these theories. Okay, so that's basically going to be the goal. So the idea is that you have liquid here, it's evaporating, and then these bubbles are in a metastable state. What that means is that if any charged particle passes through it, it will basically condense that bubble and make a little droplet that then we can see. Okay, and that's basically the principle that many of these detectors are based on. That when a charged particle passes through, it ionizes this material, this gas.
If you look at the rod down here, you can see the rod right now. See this rod down here?
Yeah. Oh, you can see that coming out of there. Okay.
That's the material. That's just.
That's right. Yeah, I see that.
This is actually wrong. That should.
That's right. It is over there. Yeah.
Yeah, that thing actually should. Whoever built this is not right.
Yeah.
I didn't build it.
Okay, so if you can come in, you can see it. You can see these little, particles coming out. You see that in this little rod down there. You see those traces as they go off. Yeah, you can circle. You have to be much closer in here. Yeah.
Just watch the rods.
So you just watch the rod down there, not the thick one here, but the one underneath it. Yeah. To the right of it. Yeah. And then what you will see is very, very little tiny traces of little droplets, and then those droplets then fall basically with gravity. Okay.
You guys see it?
Wow.
No?
That's cool.
Yeah, you see it? It's not very dense. Yeah,
On the thin rod?
Perhaps there's not a lot of... Yeah, the thin rod. You have to be looking at the thin rod. Yeah, there was a big one there, yeah.
Yeah, about
Oh.
half an inch away from it. Look at that rod.
That's right. Yeah, and then you can circle around so that
Can your
everyone
camera
gets a
pick that
chance,
up?
yeah?
Did you see it?
Yeah, so it's that rod there below, okay? So you'll see particles, coming left and right of that, okay? Now, what we have in there is a little radioactive source that is producing these electrons and alpha particles, basically. Yeah, you see that?
Yeah,
you see that? Yeah, you saw it there.
Yeah, those
right?
are big.
So those are these little traces that you can see, right? So a charged particle basically went through there and then ionized over.
The back of your head for about 30 seconds. Yeah.
Mike, don't go. I'll be right there in a minute, okay?
Oh, that's pretty cool. You should run the GoPro helmet.
That's what I was saying when we got here.
Dan, hi. Hi. This is your group. Okay. This is Professor Dan Watson.
Hi. You get to be the group that.
Oh, Tinker Toys. You guys get to play with Tinker Toys.
That's not explicitly astronomy. So that's not why we're here. At any rate, sorry, I'm a couple of minutes.
That's
late
fine.
with
That's fine. Don't worry.
Serious rat student issue. But we're about to traipse down the hall and let me show you some things having to do with astronomy. And I was going to stick these up at the end of our path. So let me get. Stick around for these.
Yeah, so now you get to see a little bit of astronomy and then optic.
15 minutes?
Sorry?
Are they-
Yeah, it's around
they're-
15 minute
they're-
each.
They're arriving at 15-minute intervals.
Yeah, it's more or less 15
And
minutes.
this is the first one, the one that was supposed to be here 7.5 minutes.
That's right. That's, I apologize for that.
Okay, we're stuck in traffic. Okay, come on.
All right.
Yeah, actually, I was too.
There's a wall there.
Hey, Carly.
Let's stop here
Careful.
and fan along the wall.
This one?
Hey, got that on video.
Oh, I get
In the
it.
midst of all these
Strictly
things, you can stretch a phase telescope and what we can do with it. Dan is me, so you get to ask me about it if you want.
Oh, it's free. You don't have to pay.
No, I know. Let's put it over here. Here's. Actually, I can. I'll offend Ian, but actually I can illustrate some of this on this poster too. Here's one of the things that you can get if you take a protostar, something that in which the center is already collapsed and made something like a star, and around which something is also gravitational collapsing and making something like a disk around the star that may someday turn into a planetary system, but which still has a lot of material in a roundish envelope, we call it, around the system that is still in the act of falling onto the disk and star and protostar in the middle. We call these things protostars because they still have a lot of weight to gain on their way to really becoming a star. I should have got the current version of this poster. Anyway, if you stick one of these protostars on the entrance to our spectrometer on Spitzer, you often see, and then what a spectrometer is something that sorts light very finely according to wavelength. You might see its brightness vary with wavelength like this. See all these spikes sticking up? The spikes just mean that at, for example, a wavelength of 24.24 microns, it's very much brighter than it is at nearby wavelengths. The reason for that is that wavelength happens to be an energy level change in neutral atomic sulfur. There's another line in here that is a similar energy level change in singly ionized silicon. Those are the only two I've labeled in here because, apart from these down here, because there are a whole bunch of other spikes in here that you can see that are similar in size to these two atomic transitions. I didn't label them because they're all the same. They're all transitions of water, the molecule water. The reason it's so bright is that this is actually material that is falling from the envelope, freely falling from the envelope of this protostar and landing on the surface of the brand new disk that is forming in the center of this protostar and in orbit around the compact object in the middle that will someday be a star. From the brightness of these spikes that have to do with water, we can figure out how much water per unit time, how many water molecules per unit time are falling on the surface of this disk. From the brightness of this line and this line, we can actually figure out how much material is actually being flung out as a result of needing to balance both energy and momentum and spin as this gravitational collapse process takes place. The result is that we have, from just the relative brightnesses of all these lines, a measurement of how much is landing on the disk, how much is moving from the disk to the compact object in the middle, and how much in its efforts to fall onto the object in the middle, the star, is actually missing and being flung out of the system. These kinds of outflows are common to lots of compact objects in astrophysics. The point is we can measure these flow rates from all these spectral lines and do things like plot the outflow rate as a function of the accretion rate onto the star, or the rate at which things are falling onto the envelope, from the envelope onto the disk, versus the sum of what's flowing out of the disk. And here's the interesting punchline here. We've measured the rate at which things are falling from envelope onto disk, measured the rates at which things are flowing out of the disk. All the objects should lie on this red line if those flows balance. They don't. In all cases, there's more falling onto the disk than there is exiting the disk. It means that the disk in the middle of this protostellar object is kind of functioning like the bucket at Seabreeze that fills up with water and then eventually, as it overbalances, tips over and dumps water out onto you. The way that the star in the middle is growing is not by constantly sipping from a straw the material around it. What happens is that the disk of material around the star accumulates material until it becomes unstable in a fluid mechanical sense, and after that it dumps the stuff all down onto down to the center. This is kind of a revolutionary result in star formation. It means that stars grow in episodes rather than a little bit at a time. They grow with gulps instead of sips. But all of that I'm using as a concrete example for why you might want to take light at infrared wavelengths and sort it so finely according to wavelength to reveal emission by specific atoms and molecules that we can use to measure the rates at which things are flowing around in circumstellar space. Okay, that'll do for my concrete example. What would you like to ask about? Jason, about how this works.
We haven't talked about the photoelectric effect, but can you tell them how the photodetectors?
Yeah, so we, in order to amplify the signal, we have to take advantage of the photoelectric effect, which is what won Einstein's Nobel Prize, actually. And so it's related to the fact that a photon, a light particle, has momentum. And I said light particle, and you think of light as a wave, but wave-particle duality, it can also behave as a particle. And so when light is incident on a surface, it can actually eject electrons by transferring momentum, has enough energy that can kick out electrons. And if we apply a big voltage between two metallic plates, then those electrons will be accelerated towards, electrons have negative charge. So if we apply a big positive charge to one plate and a negative charge to another plate, they're going to be repulsed by the negative plate and attracted to the positive plate. So they'll collide really hard into the positive plate and kick off a bunch more electrons. And those electrons, there's now another positive plate, and they get accelerated more. So you just get this big avalanche effect where the signal that you get at the end is big enough to record. and the signal that you started with was one single photon or one electron, so really tiny. And we can't really do physics with you can't measure it. And the really nice thing is you can apply. There's a certain space of voltages that you can apply these PFDs. The signal that you get out is proportional to the energy.
Did you show the picture of at CERN the eye security test?
No, I didn't.
Oh, you didn't? Oh.
I didn't.
Angels and demons. Did you guys see
I didn't show that. Yeah, we have a picture of the dog, which is this guy. So actually, to enter the tunnel, you need to like scan your retina, and it's kind of very cool. It's completely unnecessary. So the idea is that you cannot access the tunnel when there's radiation in it. There's all these protons when they're circulating. They can make the concrete around it a little bit hot, meaning radioactive. And so the idea is, to prevent that, then you need to actually have an eye scan that only allows certain people that have done all the training, basically, get through. So you have to do that, basically, if you want to do any repairs inside the detector, basically. So that's kind of cool, And this is a typical thing that I guess that, perhaps someone at CERN saw the movie or something and then say, okay, we're going to do that,
Forget, I guess some like angles.
Yeah, you have to record it on it. I'll go over here. We're the C team. Oh.
Because I think there was a mistake and I got A and B. Is that what happened?
Yeah, you should take them.
Does that make sense?
Yeah, no, you should take them.
We could come up and see you afterwards, or no?
Just go.
Okay. I'm so confused. You're recording this, bro?
Yes,
Yeah.
we are C.
You stay over there. We're the C team.
Why?
Yeah.
Zenith Radio main Rochester.
Don't walk in the wall again. That's freaking awesome.
It's Misty.
So where did you go before?
Astronomy was the satellites always off.
You haven't done the optics or
No, not. We kind of kind of avoid it.
Okay.
The kids blame me, I blame the kids.
Yeah, the teacher likes it. Smaller
on the side right here.
This one? Oh yeah.
Right.
Oh yeah, right.
Oh,
yeah, I've seen that
well, I'm
picture
at
before.
left of the.
It's right in our
the two.
classroom. Oh, and Two Faces of Light. I love that picture. Idiot.
We're going down there.
These are art students. They're doing a documentary for World War I.
Yeah.
Really?
Really hoping it's rain. I bike to school. Oh yeah. It's kind of annoying when it rains. So it's only 2 miles, so I can see it. Why is all this stuff? So we need to go see lasers.
Yeah. Do you have a laser pointer?
No, we're better than that. We have real lasers. Come on. You can step on that. That's actually to keep the dirt in the hallway on that rather than in the room. So come on in. I know that's fun. So it keeps the dust down. So I do ask that you don't like touch stuff on the tables.
I asked that too all the
Okay.
time when they walk across.
This is Julian. He also is in the lab. Great. So why don't you come around this way? Do you want to do a small thing? I'll make you.
Well, it doesn't matter. If you've got them, that's fine with me. It's up to you. I'll be here if anyone's.
Okay, okay.
3 video cameras? Are you serious?
That's what we do.
This is enough for video cameras.
We need all the different
Alright, so
angles.
I'm I'm working on a couple different experiments here. This is the one I'll talk to you about right now. So how many of you know how a laser works?
Nobody.
Nobody, okay.
A little bit.
It's good to be honest, right? Okay, I'm going to have you turn around, look at the picture board here. I'll draw a picture. So, what grade are you in? Or
11.
11?
We haven't done optics yet.
Okay, well, it's okay. I don't think I did lasers in high school, so I'm not expecting, but just wondering. So, you may have seen energy level diagrams, or you may not have. You may have seen this picture. We have a nucleus and an atom and like electrons and orbitals, right? Maybe
We just
chemistry.
talked about that.
Okay, so the quantum thing is saying, well, they have to be in different energy levels. They can't just be anywhere between, right? And this one has more energy than an electron here, right? So another way of drawing this picture is to have just lines here with increasing energy. Okay, so in a laser, what we have is the material. We excite the electrons up to a high energy state here, and then we send in some light that matches the energy difference. So there's a relationship between energy and wavelength, right? So electrons down here, if they absorb a photon, they would jump up here, and if they give off a photon, they would go down, right? So when they lose energy, they give photons, right? So that's kind of the principle that all this operates on. So in a laser, we make a bunch of electrons kind of stuck up in a level, and then we stimulate them, and they all jump down at once and give off lots of light that's all of the same wavelength, and it's all in phase. So if you have a laser pointer, that's what's happening there. And the cool thing about it is all the same wavelength, right? And it's also in phase, which is awesome.
And in phase, you know what that means in phase, remember from waves? Right?
Yeah.
Constructive
Yeah, one
interference,
wave,
all in the same phase.
every single one. So they all started at the same time, kind of thing. That's why. Right? Okay. So, and what I'm working with is a 780 nanometer light, which I don't know if you know the visible spectrum, but that is outside of what our eyes can see. Okay. So what I use is this little card here. I have a prettier looking one, but this one actually intentionally has holes in it, believe it or not. So what I do is I can put this card in the path of the beam. You can see my laser is actually on because the electrons get excited in here and they emit light that's visible to us, right? So that's how I can figure out where my beam is, even though I can't see it, right? Okay, so what I do is send laser through here, mirrors into this thing. Now, this is a fiber optic cable. Have you heard of total internal reflection? No, maybe.
No.
Okay, so basically what happens is, normally, say you have light that goes through, hits glass, like a window, it goes through, right? But if the light came at a steep enough angle, it actually reflects off, right? And so these things are designed with just the right diameter of it's like a glass wire, basically. So that none of the light goes out, it all gets reflected in, it just keeps bouncing around inside.
Yes.
And that's how like internet works, right? That's why internet can be so fast, because it goes in fiber optic cables. It like travels really fast. So it goes through this yellow cable over here, and then it comes out over here, and goes into a cell here with rubidium atoms. Okay, so I'm going to take you over to the board for a second. Not the close.
Well,
So,
are you also going to come for the second group?
Yeah, I think she was going to do this one.
Okay.
I don't. Is there a second group?
Yeah, Williamson A.
At
then-
12:25.
This is a quick sneak.
Yeah.
Okay.
This was
Oh, I see.
Then we're going
Okay.
up to the teaching lab.
Oh, okay.
Well, if they're
So
waiting, we
it's
have two
quarter after.
labs too.
No, she didn't. Connie didn't want him to start. Oh wait.
Yeah, you kind of want us to start until
12:45.
Yeah.
I see.
So
Okay,
you're
so
doing
this
the
is
next
because you missed it before.
Okay.
Okay.
Okay. Thanks.
Okay. So remember the picture with the levels. Well, in rubidium, we have the same kind of thing. And we actually have multiple levels, right? So electrons are sitting down here and here, right? At the lower
I'll
energy.
bring the other group down,
Okay.
and then we can switch.
Sounds good. And so when a laser comes in, you can imagine that it would get absorbed at just the right wavelengths that would match the energy differences. Does that kind of make sense? Sure.
More or less.
So because the electrons are going up, and every time electron goes up, a photon gets absorbed. Have you heard of photons?
Yeah.
Little packets of light. Okay. It's the quantum part that you So if I were to send the laser into my medium, I would expect that at a certain frequency that related to this difference, there would be a dip in the amount that came out afterwards, right? So if I were to plot, a wavelength, lambda, and like the amount of light we got through the transmitted light, I expect to see a dip corresponding to this wavelength here, right? And then this rubidium has multiple levels, so I expect to see 2 dips actually. There's different options. Do any of you know what an isotope is?
Yeah.
What's an isotope?
It's like a different mass or more protons or something.
Right, more neutrons.
Neutrons.
Yep.
Whatever.
That's good. That's good. So right, nucleus has protons and neutrons, right? So what that does is that affects the levels. And so we actually have another. If we had a different isotope, it would look a little bit different. We have 7 different wavelengths that would match up. So rubidium actually comes in 2 isotopes, and in my gas I have both. So I should expect to see 1, 2, 3, 4 dips as I scan through. So now we can look at the actual setup. So this plot here is a frequency, and then it dips down. I can zoom out, I guess, a little bit. Makes it more confusing. 1, 2, 3, 4 times. Okay, so that's basically the laser light coming through, hitting this detector over here, and then the detector goes through a cable over to that oscilloscope. So that's kind of about the experiment. Do you have questions about this or anything else?
What do you do it for?
What do I do for?
Yeah.
Good call.
So I could get that picture without this whole insane thing, right? That's kind of what this is, just a little setup for that. I actually have 2 lasers, and I send another laser through that sets up another standing wave in the medium, and I'm looking at a whole other effect due to that, which I don't know if you want me to go into, but basically, you can think of it as we can kind of recreate a structure that people can create like on chips with a solid thing in a hot gas. And so that's cool because we can just like turn a knob and change it in time, turn it on and off. We don't have to like go to this like huge lab and create a tiny little thing. So that's one of the things. Another thing over here is like, we can show you another experiment. You can walk around if you want. Easier to understand.
Are these all your setups? The whole table? No.
Bethany, yeah.
Oh yeah, it is?
Bethany's.
Well,
Let's
that's
count them.
setup.
Let's count them. 1, 2, 3. I actually have a whole room.
See, I was asking him when I came in. I said, "Is this a setup or is this just stuff sitting on the table?"
No,
And they're
that's
like,
all. That's for getting. Yeah, that's a setup over there. So, that one's so hard to explain that I usually prefer to explain that one.
Are you going to show us this one too, or?
You can walk by it. I can show it to you.
All right.
You can look at it.
Yeah.
I don't know if it makes sense. This one makes a little more sense. Actually, here's a fiber optic cable coming from my other setup over there. And so there's light with different wavelengths comes in. So you all know what a prism does, right? What does a prism do?
Reflects light or something.
It reflects it. What else does it do?
Separates them.
Separates, right? You get different colors, right? So actually prisms are great, but they don't actually separate out very much. So in the visible spectrum, we can see all the colors, but what if we wanted to tell the difference between one type of blue and another type of blue, you know what I mean? So what this is kind of like a prism shape. You have to come and see it. It's wrapped in a heating rope that gets really hot. The reason we heat things up is it makes the atoms move around really quickly, so that there's more in the way of a laser beam. But it's kind of like a wedge shape. And so we can separate out frequencies of light that are very close together. And then it goes along here. This is actually a camera. So it's the camera, and then it goes. I took the wire away because it's going across, but it goes over to the computer to figure out what we have, what frequencies we have. So there's rubidium inside this little glass thing. And that's why it's such a good separator, because of some of the physics that goes on there. Yeah.
Idiot.
Yeah. Well, we can walk by and see what it is. This one has one laser that I split into two, and then I changed the frequency of one of the
Mine's
arms.
gonna die soon.
Actually, I changed the frequency of two after that too.
I've been going
Yeah,
for
so
13 minutes.
Sectors.
Now, when you turn it on, can you see the laser going through there, or is it
Not
just
without a
without a card?
Yeah. So all this is
It's not working good.
Don't do
Yeah, I was. I don't think there's in here, but over there I have a. I use this as a beam stop sometimes when it's not a very strong beam. But if it is a strong beam and I forget about that, it actually starts to burn it. So here there's some burn marks on the other ones. But I don't have the strong ones on right now. Yeah. So this setup takes a really long time to align. It's really,
That's like it works.
Now, when you were saying you have to use a beam card, I mean, I understand you want particles on any of this. Is there any easier way to try and align the beams than to go like this through every little piece? Or no?
No, not really. I mean, so sometimes you can use a camera, and like actually, for example, here. So there's actually rubidium inside this, a little cell in the middle. And what I want to do is I want to have two beads overlapping very precisely over the middle. And so what I do is sometimes I send it over here, out here, where it's kind of like I can see it. Well, not with my hands. And sometimes I put a camera here and a camera here, and I go back and forth and try to make sure it's where I want it to be.
You look through this on a camera and you can see the beam.
I actually use, so I pointed out over there that black thing is that it basically shows a picture of the intensity of the beam across the space.
How long would it take you to set up this?
Well,
or is it still being set up?
No, it's set up. I took data with it earlier in the week. When I started working with it, somebody had already been working on it for a couple years. But he didn't set it up. It didn't take a couple days to set up, right? I mean, like I can go through and realign the whole thing in a day.
Okay.
Now that I know what's going on. When I first started, it would take me a week. You know what I mean? So it's just because if something will go wrong down here, and I have to figure out what went wrong. Everything's moving with temperature, right? That's what we have this big thing, right? It's not constant. Things expand and contract, and that means that your beam moves. And for moves a millimeter, that's a big deal.
Everything has to be bolted down.
These are also these tables. You see if I click on it, it shows like that. These are hydraulics. I guess they're hydraulics, yeah. Tables. So we don't like things moving around, right? So this, if I hit it, vibrations will go away, right?
Is this floor specially designed or no? Is there something wrong with the fact that they have like the air going on so close to the experiment? Okay.
Time to trade. Time to trade, Alex.
Alright, let's get a good people out here.
Thank you very much.
Yep.
Thanks.
Okay.
This way.
That way.
Thank you.
Okay.
Just shut it off.
Next.
Just take that away from him.
This way. Videotape me doing it in the bathroom.
Oh, yeah.
Up here.
These kids up here.
And he's trying to prove his innocence.
Yeah. Very good.
With a diesel.
No, I think we're just gonna take everybody in here. It's a good thing I didn't give this key back. I could've got $20 for it. Okay, you can go file in.
You guys are excited by a large tank of nitrogen?
Yeah, sweet. I'm excited about it.
Did I tell you over in Formula, I showed you that picture, they have like a school buses, like a ton of them, say liquid argon and liquid nitrogen.
Okay. So this is one of our advanced lab rooms. So this is a senior undergrad class, and they get to do a bunch of different experiments, and they're pretty cool experiments. And some of them are sort of 50-year-old Nobel Prize experiments. So I'll tell you about some of them. And so Eric is actually the expert here, so I'll see if he wants to come tell you about that. And I'll show you this.
Lasers.
We got more lasers in here, guys.
Yes,
You
dangerous.
can come actually around here so you can see the laser.
Go on,
beam a
walk
little
in.
bit better.
Just don't look at it.
This is not going to do you much damage.
I'm looking at it.
Stick your eye in that, Kyle.
So this experiment is it's called Berry's phase, and the basic gist is we start with just a laser beam from a 30 milliwatt red light laser, obviously. We polarize the beam. The polarizer is actually not in the beam line right now, but this is the polarizer. It would go there.
You guys know what a polarizer
You guys
is?
done
No, we
light
haven't done
polarization?
optics
Okay. So you can sort of think about it as there's this property of light which can be polar. I'm not going to talk about circular polarization for right now. It points in a specific direction, and so you can sort of select the light to be polarized in a certain way. And if I, suppose I say I want all the light to be polarized like this, and then I take another polarizer right after it, and I select for orthogonal polarization, no light will get through, because those two polarizations have no overlap. You can sort of think of it, if you're pointing up, you can't also be pointing to the left. And so what we do in this experiment is we select polarization in one direction, and then on the other end of this fiber, single mode fiber, we have a polarizer which I can actually just rotate. And so what you can do is align this polarizer so that no light gets through. And then this is just a photodetector, so it kind of detects the strength of the laser beam, how much light gets through. And it's hooked up to that oscilloscope. So if I measure no light signal on the oscilloscope, that means that the polarization of the light that's going into this polarizer is orthogonal to whatever direction I select. And so I'll sit here and fiddle with this until my signal is completely minimized. I have no light getting through. And now I know what the polarization of this outgoing beam is. And I also know what the polarization of the incoming beam is. And then what you can do is actually measure a shift in the polarization due to transversing this this helix in the optical fiber. And the reason why you get the polarization shift is quantum and probably beyond the scope of this discussion. But it's because in the momentum space of the light, it is going around in a circle, and the polarization shift is actually related to the solid angle that's subtended by the light in momentum space. And it's a purely quantum mechanical effect that you can observe in a laboratory like as an undergraduate, which is pretty cool. And
Do you know a lot about this?
No.
No. I was going to ask you if there was some context to the optic fiber being twisted that could shift the
So
polarization.
I don't know if there's any sort of classical way to look at it, because
Just crazy quantum.
yeah. So when you're talking about polarization of the light, you can look at the width of the fiber, and the light's actually kind of bouncing around in the fiber. But that's the momentum. That's the K vector of polarization.
That makes sense.
So it's actually the angle, and I can rotate this. But it's also important, as it turns out, that the fiber be taut. But you don't want to pull it too tight or you'll break it. So and then the other thing, whenever you do an experiment like this, you can calculate what the resonant modes are for that flask and generate those waves.
Acoustic or?
These are acoustic.
So you guys remember acoustic resonance? Remember when I hummed in the salt dance remember when the salt was dancing on the can, you guys laughed at me?
Acoustic resonance here, you amplify it with this fantastic, probably early 90s Radio Shack amplifier. You can monitor the signal on your oscilloscope, and then you will trap a little bubble. So you take really pure water, inject a bubble into it, and then use the acoustic waves to trap it in the center of your flask. And if you hit it at exactly the right frequency, the bubble will rapidly collapse, and it will then oscillate. It'll resonate, and you will get optical photons.
Would you be able to run it for us, or?
No, I don't have the pure water, and it takes probably an hour to get the thing all calibrated. But the reason why we have this dark box is so you're basically taking acoustic waves and transforming them into optical light. But the amount of photons is so small that you can't just look at it. So we get this dark box, and we have a low light camera which can take a long exposure, and then if you integrate a bunch of frames, you can eventually see the little optical spot in the middle of the flask. So it's pretty cool. It's not an easy experiment to set up because you have to find the resonant modes and you have to trap the bubbles, and it's
So is it the sound energy is creating photon release from the atoms? Or?
So actually the actual method of sonoluminescence is not well understood, and there is a lot of debate in,
so I just won the Nobel Prize, write that down.
So the explanations, there's even a school of thought that says that it's due to Hawking radiation. So that it's not well modeled. There isn't they kind of understand how the bubble collapses and then how it oscillates in a resonant mode, but they don't. It's not fully understood how where you're getting optical photons. Then the other experiment we have set up in here is this electron spin resonance lab, and so this is a really old klystron and a bunch of waveguides. In fact,
can you explain to them what an electron spin is?
Sure. So it isn't spin. There is a property of an electron, which is, do you know what angular momentum is roughly? Okay. So you can imagine if you have an electron, classically it's orbiting around a nucleus in an atom, and so it has some orbital angular momentum. But that's actually not all of the angular momentum that we observe in an electron. So there's this intrinsic angular momentum, which you can kind of classically think about that as it's the angular momentum that you would get from the electron spinning while it orbits. So like for instance, Earth has orbital angular momentum in its trajectory around the sun, and there's also angular momentum in the way the Earth spins. And if you really naively said, well, an electron in an atom is just like a planet, then you would get spin, and it would be actually the electron spinning. In real life, you cannot think about electrons spinning, and they don't classically orbit. And it's a lot more complicated and probabilistic and quantum mechanical states and stuff like that. But you just have to think of spin as this property that electrons have. And so what we're trying to do in this lab is we're going to measure the relationship between the magnetic moment of this electron, which is just is basically this spin, and the angular momentum. And there's this constant which you just measure experimentally, called the Landy G factor, and that's sort of the goal measurement. And so what we want to do is get to this resonance equation down here, where at resonance, the G factor, this mu B is a constant called the Bohr magneton, H is the applied magnetic field, little h is Planck's constant, and nu is the frequency. And you can measure the applied magnetic field with this Gauss meter. So you apply a big magnetic field on your sample here and measure it with the Gauss meter. This little tube is how you measure the frequency. So basically, the klystron is going to generate microwaves. And so microwaves, in this case, the wavelength is a couple centimeters. And so it takes probably a little getting used to from someone with your background to think of waves as having a wavelength of centimeters. Radio waves have wavelengths of kilometers. Light has nanometers. But this is actually a couple centimeters of electromagnetic radiation. And so it's really important that this whole waveguide be exactly the right length. So you're going to have your signal that's going to come down here, and you can actually tune the cavity length with this knob. So if the cavity is a little bit too long and you are not at a node at the end of the cavity, then you're actually going to get interference that's going to ruin your signal. But if the cavity is exactly the right length, you have a wave coming in and hits one of the nodes at the cavity, then you'll just interfere constructively.
Is this a direct magnetic field north to south or something?
This is it's actually just in here, but this is it's just a solenoid with. So you have a bunch of coils. We run a big old current through there, and then you get a fairly uniform field, and I don't remember which direction it goes. And you could make it go in different directions by just the sign of the current. But yeah, so when if you have a bunch of coils, whenever you have current moving through a wire, the magnetic field is going to loop around the current. And so if you have a bunch of coils and you add up the magnetic field from each wire, you get this effect where it cancels basically everywhere except right in the center of these two coils. It's going to add in the same direction. So that's how you get your uniform magnetic field. That's fairly standard. Like you'll do, if you take physics in college, you will undoubtedly encounter an experiment where you use a Helmholtz coil to generate a uniform magnetic field. And the B field is, it's not so strong that, like, I think I could put my credit card in there and be safe, but I wouldn't want to try.
Could you put this under someone's office desk and waste their computer?
Probably not. Well, certainly not. Because the magnetic field, the other nice thing about a Helmholtz coil is the field is really isolated to between the coils. It cancels just about everywhere.
It doesn't warp out.
It doesn't do anything like that. So I'm going to take a spicetron, generate microwaves. I'm going to split the microwave beam here. I'm going to send half the beam here. This is my reference signal. And then I'm going to send the other half of the beam down to this to a sample, and then it's going to come back up and then come around in. So one of it goes here, the other one comes in here, and then I have this. I can take the sum and the difference of these two signals. I have these variable attenuators which I can adjust, which just controls basically the magnitude of the signal. So I'm actually looking at a phase. And you read this out on an oscilloscope, and so you wait, you adjust your magnetic field until you all of a sudden hit resonance, so the signal just is flat. Now well, for certain materials the resonance band is wide, but the stuff that's easiest to see, which is this DPPH.
Well, and a lot of the...
I don't even remember what that stands for. It's some chemical. Has a really narrow resonance, and so you know when you're on it, and you're just tweaking it by a tiny bit, and all of a sudden. And then you just read out measure the frequency, measure the magnetic field, and then you can get this quantum parameter from this experiment. And they did pretty well. For DPPH, they got it to within like 1% of
graduate study and the rest of
the accepted value. So.
Yes,
yeah, so that's pretty much this experiment. I don't actually know. There's a couple pieces that we don't really know what they do. This setup is so old that the manual that the manufacturer of this waveguide that came with this waveguide actually says that you should contact if you have any issues, contact them by sending a telegraph. So it literally predates.
Where do you put the DVD?
The DVD, I don't know what the point of the DVD is. This is just a blank CD. It was probably just sitting around. There's a lot of junk in these labs sometimes because the guys like Mike who run the lab, these experiments don't come in a box, right? Like Mike just built it. Mike got a camera, got a flask, and figured out how to do the experiment. We have a Stern-Gerlach experiment, which is one of the original sort of foundations of quantum mechanics experiment, which we just kind of pieced together. And so Mike is constantly looking for free crap that he can turn into science experiments. And he used to work at Kodak, and so sometimes like the Kodak labs will want to get rid of old equipment, and Mike will take it. And I kind of like fiddling around with electronics myself, and so when Mike breaks something, he'll give it to me and I go take it apart. And if I manage to fix it, then I get like a free oscilloscope or something.
So you can hook up to your stereo,
yeah. I mean, I have a multimeter that I use surprisingly often, so yeah, you get a nerdy physicist a little piece of electronics and let him go.
What are you doing?
Let's see if we can swap here.
You can shut it off.
It's full.
They actually want you to do MCC.
No, we have to go back. It's 12:50, so at 1 o'clock we have to get upstairs, so we should probably just go back upstairs.
Yep.
Let's go.
So they want that and then transfer and get your...
On the way up, can we stop at the Minerva post?
Absolutely. That's something I actually know about. So,
Taking freaking videos.
So then let's go. How should we go? I guess we should go this way.
I think they have to go back upstairs.
Following us.
Just is there?
Yeah, we were up here.
So on our way back to 407, I'm going to stop briefly and show you the experiment that I work on. So this is called Minerva. It's a neutrino detector at Fermilab outside of Chicago. And what you're looking at is one plane from our detector. And this is a real live plane. It used to be at Fermilab. It didn't perform very well, and so we got rid of it and brought it here. So here you can see, this is a good picture of the front of our detector. So this is like what a plane looks like when it's mounted with the outer detectors. And then these are photomultiplier tubes on the top, and the neutrinos come in this way. So this plane would have been just somewhere, there's 240 planes just like this, all stacked in a row. And what we're looking for is neutrinos interacting with matter. And so neutrinos are really small particles. You can sort of think of them as if the electron had a cousin, that would be the neutrino. And they don't have electric charge, and this makes them very difficult to detect, because normally when you are trying to detect interactions between two particles, if they're charged particles, well then they'll, if you have an electron, say, and you're shooting it at a nucleus, well when it gets really close to the atomic nucleus, since the electron's negative and the nucleus is positive, they'll be attracted to each other and there'll be an electromagnetic interaction. But neutrinos don't do that. And so most of the matter, the neutrinos just go straight through. And so we shoot an extremely intense beam, trillions of neutrinos, at a big detector that weighs 15 tons, and we get a few events. And so we're trying to study what these neutrinos do. And so maybe I can show you the scintillator, which is kind of cool. There's what this detector is made out of is mostly just plastic scintillator. And so there are these strips, which you can see here when we've removed this light-tight plastic. And they're just made of plastic. And so what scintillation is when there's a charged particle that's going through the detector, it will deposit a little bit of ionizing energy in this plastic, which means it'll excite atoms, and those atoms will come back to the ground state and they'll emit a photon. And that optical light is absorbed by these wavelength shifting green fibers, which are embedded in the middle of each scintillator strip. And so all through this detector, there are these green fibers, and they come out at the edge of the detector, and they go into a connector, and then to another fiber, and then to one of these photomultiplier tubes. And then we amplify the signal with the photomultiplier tube until it's basically an electronic signal, and then record that. And so we can actually get position information because we know where this plane is in the 240 plane stack that I told you about. And these strips go in this direction, and so if this strip lights up, we know that the interaction happened somewhere along this strip. So that gives us 2 dimensions, but we actually want 3-dimensional reconstruction. So what we do is the plane immediately behind this one, it shifts, its strips are going to be rotated 60 degrees. And so then you'll get the other coordinate from 2 consecutive planes. And so here's just an example of what neutrino events look like in our detector. And so you're not actually seeing neutrinos. you're seeing the charged particles that neutrinos produce in their interactions. And so how do you know that a neutrino has interacted? Well, you see nothing for a while because the neutrino is not interacting. And then all of a sudden you see charged particles. And the charged particles don't just appear, they come from the neutrino interaction. And so you're going to be talking a lot about muons and electrons when you do this data analysis from CMS data. And so I can show you, this is what a muon looks like in Minerva. It just makes a really long track, and that's the same thing that will happen in CMS. The muons go all the way out through all of the inner detectors and the calorimeters, and then you have these things they call muon range detectors, which exist for the sole purpose of detecting muons. And this is what an electron would look like. It just makes a fuzzy little shower of energy. And so in CMS they have a dedicated calorimeter which is designed to just detect the electrons. So this is actually a cool event. So the neutrino came and made a muon, and then this two adjacent electrons is another particle called a neutral pion, pi 0. And that particle is very short-lived, and it immediately decays into two photons. And those photons will produce electron showers. So when you see two showers like this that come from the same point, you can trace them back to the same vertex. That's how we know that that was a pi 0 in the detector. So this detector is capable of not just measuring that there was a neutrino, but measuring specifically what particles came out of that neutrino interaction to a very good precision that has not been attained before. So that is what we have. What time is it?
Noon! We got this, dude.
Alright. So, Jameson, what should I click?
Just start clicking stuff on.
All right, so are you guys there?
Kind of. How do we clean it up again?
Unclick that off. Unclick that off. What are you doing?
Yeah, so you guys have to clean up the track, so you have to go all the way down, and then click on missing over these spots. That's the last one. There you'll see are you sure you haven't cleaned anything else?
Yes. Leave it like that when the guy walks.
Actually, why don't you start again?
You might spaz out.
All right, so
Something that was clicked.
You have to click the top one off too. Oh great, now I don't know which one.
okay, so please.
Supposed to be freaking on.
We got 3?
Oh, we got more. We got way more than 3.
We got 3. We got 13.
So Chris, what did you think of this event analysis?
For the tau and I mean not for the tau, for the other two that were available from the selections, what was it, the pi naught and I did the other two particles, the j psi and the epsilon. For those we asked them and bought them and they told us like what those kind of looked like, so then we were able to kind of eliminate those if those kind of signs appeared. For the other ones, not so much. A lot of them just seem to be maybe combinations or both, or there's lots of different mixed kind of signals.
Oh, the future physicist talking.
Oh, we all are. Okay, so this, we're at the end of our allotted time. If you want to stick around and talk a bit, we can. But if you need to go, that's fine too. So that's up to you. I know these guys are going to take a tour of Fermilab in about 10 minutes, but they'll hang around until then.
You had that one question that you asked them at the beginning. Oh yeah, the circumference thing. Yeah.
Sorry?
The longest question. Yeah, the longest
I've got to come back to you about how many times around the protons go.
11,000.
Did you get an answer?
11,000.
Yeah, they got it right. It's 11,000.
Yeah, we know.
They're yelling.
You guys are better than I am. I usually just round things off and come up with 10,000.
Hey, science is real.
Yeah, see, I make 27 into 30 because I can't resist canceling out those threes. Good work. So you imagine how many collisions are happening all the time that the software at CMS and Atlas have to deal with. I'm glad I'm not writing that code because I wouldn't know how. Okay.
A lot of effort from all of the words, kind of
Right.
timing, and so making all the combining all the facilities, computing facilities, all of the world is doing
A
together.
major CMS data center right here.
Right.
Just handling all the, whatever comes out of the firehose.
Ken, can I ask you a question, Ken? Ken?
Yes.
It's Friday at Fermilab right now, right?
Yes.
I
Yes.
think so.
How come you're not
Yes,
having?
we are making it sacrifice.
Yeah, no
Go
wine
on.
and cheese? Where's the wine and cheese?
Let's go that way.
While we're away.
Oh, we're in New York. It's wine and cheese time here.
Well, don't let us stop you, but I think probably we'll keep the students out of that.
Yeah, they're underage.
I like the cheese part though.
You should stick in and eat the crackers.
So are you going to give the students cheese?
Yeah, we gave them cheese earlier. They had cheese. Who likes cheese?